Okay, we've seen simple harmonic motion. You have net force equals negative kx, where x is your position relative to equilibrium position. And that leads to the function x of t equals a cosine of quantity omega t plus phi. We've seen this, where omega equals the square root of k over m. And this is verifiable. This is the function that you could put into this equation. Net force is mass times acceleration. Acceleration will be the second derivative of this function. And the second derivative of this function, when multiplied by the mass, gives you negative k times this function, negative kx. Once you have this, whether you can derive it or just memorize it, you can easily calculate velocity and acceleration by taking the first derivative to get velocity, second derivative, or the first derivative of the velocity function to get the acceleration function. And then you do want to check this. F net equals negative kx means mx double prime equals negative kx. And x double prime is this, so the mass times this acceleration function should equal negative k times the position function. And it does, because omega is the square root of k over m, so omega squared is k over m, so we place omega squared with k over m, and multiply by m. You're going to lose these m's. They're just going to have negative ka cosine of omega t plus phi, which is what's on this side. So you have equality, and the answer then is yes, it checks. Okay, and that's, again, just a review. I think we did all that previously. Now let's take the example of a pendulum. Got a pendulum of length L with a mass m on the end of it. Okay, now it's a sloppy diagram, but we've analyzed this diagram to figure out what the net force in this case is when the mass is at distance x from its equilibrium position. And we've seen that that net force is negative mgx over L. It's been a while and you might not remember, but we did it. And you're going to see it again when you work the chapter. And of course, that's going to be equal to negative kx if we let k be mg over L. Okay, so F net is negative kx where k is mg over L. Now we have our force constant, and we can calculate our angular frequency, square root of k over m. Okay, pendulum then is an approximate simple harmonic oscillator. Now notice that I don't have an equal sign here, it's an approximately equal, and if you remember the reasons for the approximation, it's simply that the pendulum doesn't follow a straight path, it follows an arc, and the analysis of the forces on the pendulum assume a small displacement from equilibrium so that the arc is very close to a straight line. The fact that the arc isn't a straight line has implications that make this only an approximation. Okay, well anyhow, the pendulum then is a simple harmonic oscillator with a mass of m and a force constant mg over L. So the equation of motion is, well, x of t equals a cosine of omega t plus phi, where omega is the square root of k over m, but that's just square root of mg over L divided by m. The m's divide out, you end up with just the square root of g over L. So there's omega for any pendulum in terms of its length. Mass makes no difference. You just saw it divide out. Now, if you know the length, then you have only two unknowns in this equation, a and phi. You need two pieces of information for a given situation with a pendulum in order to solve for A and phi. Okay, simplest situation, pendulum of length 60 centimeters, let's say. And you pull it back to some distance and release it. It's going to move in simple harmonic motion, the amplitude equal to the distance of the pullback from equilibrium. So what's the equation of motion? Well, in this case, the distance of your pullback will be the amplitude, so we have already evaluated A. And you understand that if A is 10 centimeters, then since the cosine function goes from -1 to 1 to -1 to 1, keeps going between -1 and 1, that x of t is going to go from -10 centimeters to +10 centimeters and so forth. So A is 10 centimeters. Omega is the square root of G over L. And we can evaluate that. That's not an unknown. We have the information to calculate it. Because we know the length. So we just do that square root and we get something pretty close to 4 radians per second. Just a little more than 4 radians per second. We conclude then that x is 10 centimeters, that's your A, times the cosine of omega t, omega being 4 radians per second, plus phi. Now we still don't know phi. In any case, and then I say that, well, phi is 0, but here's why phi is 0 in this case. Okay, now this takes a little bit of analysis, but actually not that much. Okay. X of 0 when t equals 0, assuming that we release it at 10 centimeters at the t equals 0 instant, x of 0 is then 10 centimeters. And of course x of 0, well, okay, x of 0 is 10 centimeters. So if we plug into the equation where we already know that A is 10 centimeters, we get 10 centimeters, x of 0 equals 10 centimeters times the cosine of, well, t is 0, so that 4 radians per second times t is 0 plus phi. So this is just 10 centimeters equals 10 centimeters times the cosine of phi. Okay, well, cosine of phi then is 1. We just divide both sides by 10 centimeters. Cosine of phi is 1, so phi is 0. Or if you want 2 pi, 4 pi, 6 pi, even multiple of pi, but between 0 and 2 pi, phi is 0. Okay. Then that gives us the equation of motion for this pendulum, which now is going to be 10 centimeters times the cosine of the quantity 4 radians per second times t. Written kind of small, that says radians over seconds. Everything else should be legible. And at this point, after determining phi as t, we just kind of draw the arrow through phi, say it's 0, so we don't have to write it. That's the equation of motion. And now that you have the equation of motion, you can figure out the velocity at any time. Just take the derivative of this expression, you get the velocity. If you want the acceleration at any instant, you just take the derivative and you get the acceleration. Let's look at another example for a pendulum where we have a little more work to do. So here we have a pendulum of length L. Presumably this is vertical, but when I look at it, I miss by a little bit. We start at equilibrium though. And we give it a velocity v0. Okay, so maybe this thing is a hanging billiard ball. It's just hanging there. You've just got an impulse to walk up with a cue stick and hit it. Okay, so we give it a velocity v0. Whatever. Somehow we give the thing a velocity v0 at the equilibrium position. Well then, what do we know? We know that x at 0 is 0, assuming, again, that t equals 0 when you hit the thing. Okay? X of 0 is 0 because you're starting at position 0. Position is 0 when time is 0. V of 0, velocity at that instant that you hit it, or the instant just after the impulse has been delivered, is going to be V naught. Okay? Now, it didn't give you the actual velocity, but we could have given, we could have given you a length and a velocity. We'll just do it in symbols to see how it works out. Okay, two equations here. Now you know that x of t has two unknowns, a and phi. And you know that v of t has two unknowns, a and phi. Now, assuming you have enough information, you're given the mass and the length, then you can calculate omega from the length. In any case, this will be two simultaneous equations in two unknowns. And I'll circle those unknowns just to make it clear. Okay, A is unknown, phi is unknown. How are you going to determine A and phi? Well, x of 0 equals a times the cosine of omega times 0 plus phi, just plugging in 0. And x of 0 is 0, so a cosine phi is 0. Now that allows you to determine phi, sort of. We'll see in a minute. Okay, v of 0 is negative omega a sine of phi. Again, just plugging in 0 for t. And then v of 0 is what we call v sub 0, v naught. That'll be negative omega a sine phi. Well, various ways we can approach this, but in this case, we'll do it this way. A cosine phi is 0, which means that the cosine of phi is 0. The cosine of an angle is 0. Well, if you look at the circular model, on the x-axis, cosine is 1 on the positive x-axis, cosine is 0 on the negative x-axis on the unit circle. The sine is plus 1 on the positive y-axis, negative 1 on the negative y-axis. Okay, on the positive x-axis, your angle is pi over 2. Okay, the angle from the positive x-axis to the positive y-axis is pi over 2. If you want to go all the way around to the negative y-axis, the angle is 3 pi over 2. So phi has to be either pi over 2 or 3 pi over 2 in order for the cosine to be 0. Okay, omega a sine phi has to equal v naught. Now, we've already got two candidates for phi. We don't know which one we actually need to use, but that'll be easy to determine. But we're going to know sine phi. We're given v naught, and we given the length, so we can find omega. So, right here is your expression for the amplitude. And all we have to know is what the sine of phi is. Well, remember that phi is either pi over 2 or 3 pi over 2. If phi is pi over 2, then sine phi is plus 1, and a is v naught over omega. If phi is 3 pi over 2, then sine of phi is negative 1, so that a is negative v naught over omega. Now, a is positive because your amplitude is a positive number. Even though you go from the positive displacement a to a displacement of negative a is the positive number that's the amplitude, okay? So a is positive. It follows that v naught is greater than 0. Phi has to be pi over 2. Why is that? Well, if v naught is greater than 0, then since A and omega are both positive numbers, A would be negative in this case, but this is a case where phi is 3 pi over 2. So this can't be it. If V naught is positive, your only choice is for phi to be pi over 2, so that A is V naught over omega, making it positive. If V naught's positive, you got to have this. If V naught's negative, you got to have this. That means phi is negative 3 pi over 2. In this case, we said that the velocity was V naught. Well, we don't know if V naught is positive or negative. More specifically now, if our pendulum length is 60 centimeters, omega is 4 radians per second, and V naught is 10 centimeters per second, then what can we conclude? Well, first thing we conclude is since V naught is positive, phi has to be pi over 2. There are other ways to figure that out too. This is the only way to reason it out. In any case, if V naught is 10 centimeters per second, phi is pi over 2 since V naught is positive, from what we just said. And then, what's A? Well, A is then going to be V naught over omega, which is 10 centimeters per second over 4 radians per second, and that works out to 2.5 centimeters. It follows that our position function is 2.5 centimeters times the cosine of omega t plus pi over 2, and omega, I should have written that, is 4, and I wrote in my units, radians over second, kind of small, you probably can't read it. Make that R look a little more like an R, maybe you can. Okay, 4 radians per second times t plus pi over 2. You want the velocity function? Sure, v of t is just x prime of t. So it's going to be the derivative of cosine of 4 radians per second t plus pi over 2 is negative 4 radians per second times the sine of the same argument. So it's negative 4 radians per second times 2.5 centimeters times the sine of 4 radians per second times t plus pi over 2, where I've actually written out radians per second here and here where you can probably read it. And that equals then negative 10 centimeters per second, because a radian times a centimeter is a radian of angle times a centimeter of radius gives you a centimeter of arc. Negative 10 centimeters per second times sine of 4 radians per second t plus pi over 2. And that doesn't give you 10 centimeters per second when t equals 0. That's kind of interesting. I mean, this is straightforward. That shouldn't have happened. Uh-oh. Okay, shouldn't have happened. I'm glad it did, because it means that I did something really dumb here. It's negative omega a sine theta equals v naught. So a is negative v naught over omega sine theta. So if theta equals pi over 2, A is negative V naught over omega, because A has to be positive. Wait a minute, am I saying that right? Yeah. Because A is negative V naught over omega sine theta. A is negative V naught over omega when theta equals pi over 2, because sine of pi over 2 is 1. And here, A would have to be positive V naught over omega, because the sine of 3 pi over 2 is negative 1, and that would give you A equals V naught over omega. Here, A is positive, so if V naught is less than 0, phi has to be pi over 2. If V naught is greater than 0, phi has to be 3 pi over 2. Just reverses my reasoning here, because I carelessly didn't write my negative sign here. I wrote kind of a small negative sign down here, but it's big enough I should have seen it. Okay, so in checking this out, we find there's a flaw. V naught is 10 meters per second, so phi is 3 pi over 2. And that turns out to be easy to correct. We just change our pi over 2's here to 3 pi over 2's. And now it all works out. Because if t is 0, you get the sine of 0 plus 3 pi over 2, which is just 3 pi over 2. Sine of 3 pi over 2 is negative 1, which would make this positive. You got to be really careful with the signs, like I apparently wasn't. And then if you want A of t, it's V of t or x double prime of t. You want to keep reminding yourself of that relationship, because when you're first encountering this stuff, it's easy to lose track of it. But you take the derivative and you get another 4 radians per second times your negative 10 centimeters per second times the cosine of 4 radians per second times t plus 3 pi over 2. Then 4 radians per second times negative 10 centimeters per second, of course, is negative 40. Centimeters per second squared, which is a perfectly good unit for acceleration. So you have negative 40 centimeters per second squared. You can compare that to 980 centimeters per second squared, which is the acceleration of gravity, and see that you've got about 4% of the acceleration of gravity. If the cosine of this thing is 1. So, there we have it. Your acceleration function, your velocity function, your position function. Your maximum possible acceleration is 40 centimeters per second squared, and that's going to occur when the thing is out here accelerating back toward equilibrium in the positive direction. Well, let's say you release it from here. This is positive. Okay, from the perspective of the board, I've been using this as positive, but let's just say positive is here. So you pull it out to, well, you hit it with a cue stick. Give it a velocity of 10 centimeters per second. So it's here. You poke it here. Gets a velocity of 10 centimeters per second. This direction being positive. It swings back. It swings out 2.5 centimeters. Then it swings back to equilibrium, achieving a maximum velocity. Turns out to be your 10 centimeters per second, which is exactly what it should be. Then it comes out to here. Now it's starting to swing back, so it's got to have an acceleration in this direction so it can pick up velocity in this direction. And the acceleration it has at this point has magnitude of 40 centimeters per second squared. In fact, it would be 40 centimeters per second squared. Out here, it's going to accelerate back this way. Acceleration is going to be negative 40 centimeters per second squared. So there are all kinds of questions you can answer once you have these three functions. Okay, well, that'll be it on simple harmonic motion for today, and hopefully that'll do you some good when you get to that chapter.